What is the minimum value of the force F applied to move a sphere weighing 20 newtons from a ladder as shown in the figure? All right, so the idea here is we have this ball trying to push it up a step, and we're going to do some force going this direction. So normally when we're trying to find motion, if something's going to move or not, we want to find the sum of all forces and then equals mass times acceleration. And that's going to give us an acceleration or motion linearly. In this case, we're talking about rotational, so we're going to rotate this ball up the step. And so instead of doing force equals ma, we're going to use the sum of all torques, which is moment of inertia times alpha, angular acceleration. So this time, though, we're going to say the sum of all torques, and we want it to just barely start moving, so we're going to set the sum of all torques to 0, just the same way as if we wanted to find it just barely accelerating. So we're going to say this is equal to 0, and then two torques involved, so a torque is R cross F. So we're going to have two torques here. We're going to have one due to gravity, so force gravity. That's a terrible F, but it's supposed to be an F. This is a force going up that way. So we're going to have this torque that's clockwise, and this one that's going to be clockwise because it's all with relation to the pivot point over here. So this, the clockwise, is going to be R. We call this RF just to be so we know which moment arm we're talking about. Minus R, and it's going to be from the center of mass because gravity is pulling it down, cross F due to gravity. And these are all vectors. And so the idea here, and the reason is I did negative, is because it's in the opposite direction. In this case, the negative sign is just denoting direction. In this case, clockwise and counterclockwise. So then this is going to be equal to 0. So rewriting this real quick, RF cross F is going to equal R center of mass cross FG. So there's various ways of looking at cross products. The easiest one, the way we're going to look at it here, so the magnitude of a cross product of R cross F is going to be RF sine of theta, where theta is the angle between the two vectors. Another way of looking at it is we can decompose these vectors. So I'm going to redraw this real quick. So if we redraw this, and I'm just going to draw the corner here. So this is not drawn to scale. This is 0.5 high, and that's only 0.5 meters, looking at everything in meters. This is 0.2 high, so this distance here is actually 0.3 meters. I know, not drawn to scale, that's okay. So this is going to be 0.3 high. This, from where the center is to where the ball touches the pivot point, that's just going to be the radius. That's going to be 0.5. And that's going to give us a 3, 4, 5 triangle. We could do this doing angles, find the state and all that stuff, and it'll work great. But it's easier if we just recognize, all right, 3, 4, 5 triangle, or we can use Pythagorean's theorem. Either way would work. So we see this, and the two vectors we want to cross, looking at this one to start with, is R center of mass cross force of gravity. Now to do this, we want to find the angle between this vector. So it's going to be, the moment arm is this direction, so we're going to go up like this. I know, vectors are not supposed to be that squirrely. Today, they shall be. And going down that way. So we're going to do a cross product between these two vectors. Well, cross product is kind of a measure of how perpendicular things are. If two vectors are perfectly perpendicular, then their cross product is just the two vectors multiplied by each other, i.e. in this case, theta would be 90, so sine of 90 is 1. And if two vectors are parallel, this will be sine of 0. They're going to be just equal to 0. And so we can break down this moment arm into a vector that looks like this and a vector that looks like that, and then just add these two cross products. So instead of doing a cross product of this, we're going to do the cross product of this versus force gravity and the cross product of that of force gravity. It sounds complicated, making it sound harder than it actually is. So I'm going to write this as RCM. I'm going to do two little parallel lines here to show this is just the parallel portion. Cross force gravity plus R center of mass perpendicular cross force gravity. So I said before, a cross product is a measure of how perpendicular two vectors are. So when you have the cross product of two parallel vectors, this is the parallel portion right here, cross that, this is just going to be equal to 0. Because you have a cross product of two vectors that are parallel, then it's going to be 0. Dot product, exactly the opposite. The dot product is a measure of how parallel things are. So this is just going to be the perpendicular portion times gravity. And so this is going to be equal to R CM perpendicular times force gravity. At least the magnitude will be. Cross products give you a vector, but I'm going to ignore that out of convenience for right now. So if we look at R center of mass perpendicular times force gravity, the R center of mass perpendicular, the perpendicular portion is 0.4. Force gravity is 20. I think they told us that. 20 newtons. So this right here is just going to be 0.4 times 20. And we said earlier this is going to be equal to RF, the force. So the force, the idea is we want to minimize the force. So to minimize the force, we want to maximize RF, so the moment arm. And in case the moment arm here is going to be the diameter. So it's going to be 1 meter. So just 1 meter. We want to maximize the cross product, which means that this is going to be perpendicular. So it's also going to be 1. And then we're going to have our mystery force that we're trying to minimize. So therefore, force is going to be 0.4 times 20. So to simplify this a little bit, actually we need to do this math, no big deal. So 0.4 times 20 is 80, and then move the decimal point over because of the point, and we have 8 newtons. And this is how we can get our force is 8 newtons. So to backtrack real quick, what we did was we summed all the torques, set them equal to 0, and that's basically set our torques equal to each other. And then we converted this R center of mass cross force gravity to the radius to the center of mass that's perpendicular to the force times gravity. And that's why we look at just this component here, the 0.4, which was perpendicular to force gravity, which is straight down. So this 0.4 is the part that's horizontal, which makes sense because gravity is going to be vertical. So that's how I would approach this problem. Hope that helped. See you next time.